Let's do an example of binary search. So let's say we have an array of 12 elements, and let's just suppose we want to find 75 in here. Now, if we look at this, we can see that 75 does exist, so we will find it. But let's show how we can use the binary search algorithm to actually find it. So let's say we start at the very beginning. So low is going to be 0, high is going to be 11, and the key is going to be 75. So we're going to compute our mid. So we're going to do low plus high, so that's 0 plus 11. So that's going to be 11 if we divide it by 2. And that means the mid is going to be 5. Because remember, we're dealing with integer math here. So even though it's technically 5.5, we cut off the 0.5 part. So mid's going to be 5. So then we're going to compare A5 with 75. And in this case, A5 is 39, so we're comparing 39 with 75. Now, since A5 is going to be less than 75, then we know that we've guessed too low. We need to guess higher. So we need to cut off the first half of the array. So we're going to set low to be mid plus 1. So since mid is 5 and we're going to add 1 to it, low is now going to become 6. Here's our new search area. So since we don't need to check the lower half, I just chopped it off just for visual purposes. So here's our new search area. So our low is going to be 6, our high is still 11, and our key is still 75. So now we're going to compute mid again. So that's going to be 6 plus 11, so that's 17. And we divide that by 2. So that's technically 8.5, but that becomes 8 when you're dealing with integer math. So we have our mid. Now, technically, this is over to the side, but that's okay because we have an even number of elements. We're not worried about it. But our mid is 8 in this case. So now we're going to compare A8 with 75. So we're going to compare 66 with 75. And we see that A8 is less than 75. Our guess is still too low. So we need to cut off the bottom half of the array. So we're going to set low to mid plus 1 again. So since mid is 8 and we're adding 1 to it, our new low is going to be 9. Here's our new search area. So we cut off the bottom half of the array again. Our low is 9 and our high is 11. So we need to compute our mid. So that's 9 plus 11. Take that divided by 2. So that means we have 20 divided by 2. So that gives us our mid to be 10. So now we're going to compare A10 with 75. Well, A10 is 89. So we're going to compare 89 with 75. And in this case, A10 is greater than 75. So we've guessed too high. So now we need to modify our high variable. So we're going to set that to mid minus 1. So that means since our mid is 10 and we're going to subtract 1, that means our high is now 9. We've now cut off the top half of that last array. And we see here that we only have one element left. So if this isn't 75, then we're in trouble. But obviously, we're going to see that. But we still got to follow the algorithm. So let's just go ahead and just follow the motions. So we're going to compute our mid. So our low and high are both 9. So 9 plus 9 is 18. We divide it by 2. So our mid is going to be 9. So we're going to compare A9 with 75. A9 is 75. So we're going to find that A9 does equal 75. This means we have found our key, so we would return the value of mid. So we're going to return 9 as the index of where our array element contains our key. In our last example with binary search, we only needed 4 comparisons. Now, let's say we use the sequential search approach. We would have needed 9 comparisons to check all the elements of the array. Or I guess technically if you would have searched from the other direction, if you thought your value was high enough, maybe you only need fewer comparisons. But if we use our standard sequential search approach, we would need 9 comparisons. And you might think that's not really a huge improvement. Between 4 comparisons and 9 comparisons, that's not a whole lot. The reason why this is a big deal is when n becomes substantially large, this is a huge improvement. I mean, just completely huge difference between using binary search and sequential search. So what's the running time of binary search? Well, let's first consider the body of the loop. Everything inside the loop is a constant time operation. We're just simply doing some assignments, we're doing some comparisons. All those are constant time operations, so that means the body of the loop takes O of 1 time. So the question then is how many times do we actually run the loop. That's going to dictate the running time of the algorithm. We'll use an example to show the number of iterations of the loop. Let's suppose our array is of size 1024. So remember that the way this algorithm works is with each iteration of the loop, we're going to cut the size of the array by half. Now, how does that become a factor for us? Well, another way we can think of 1024 is 2 power 10. So because 1024 is 2 power 10, the while loop is going to have at most 11 iterations to determine whether or not the key is in the array. Now, how do we get 11? Because shouldn't it be 10? We have 10 iterations of the loop. Well, we find that 10 is log base 2 of 1024. Remember, we talked about some log rules a while back. So I said that it was going to come back to us. This is where it comes back. So remember that if 1024 is 2 to the 10th power, then the way we get 10 is we take log base 2 of 1024. So that's how we get the 10 part. And then we'll need one additional iteration to determine that the key is not in the array. So there would be an additional iteration of the loop to do that. So what this means is that since we're dealing with logs and log base 2, we actually have O of log n iterations. And since we've already mentioned that each iteration takes O of 1 time, the running time of binary search is O of log n.